Hello students. In our last few videos we've been talking about how there are three factors that affect the size of atoms and ions. And we're going to see those factors come in again as we're talking about a new topic in this video called ionization energy, IE. And so the first thing I'd like to mention is that ionization energy can also be referred to as ionization potential. Abbreviated IP, and they mean the exact same thing. So ionization energy, or ionization potential, they're the same thing, is the minimum energy required to remove a valence electron from an atom in the gas phase. So to clarify, if I have an atom and I'm trying to remove an electron from it so that it becomes positively charged, that requires some energy. And the energy that is required to remove an electron from an atom is its ionization energy. The phrase "in the gas phase" just means that the atom is alone by itself. It's not in a compound or in a crystal or anything. So you have an atom alone by itself and you're removing one of its electrons. The energy required to do that is the ionization energy, or the ionization potential. So let's imagine that we have an atom here and we have the nucleus, and it's down here. And then I have some electrons around that nucleus. And we know that I have the 1s and the 2s and the 2p subshells. Okay, and those are the orbitals in each of the subshells. And let's imagine that I have a lithium atom. So lithium atom has a 1s2 and a 2s1. So this is lithium, right? And now I want to convert that lithium into a lithium cation. And by doing so, this lithium has to lose an electron, so I'll also end up with an electron as the result of this process. So what I have to do is I have to lose an electron from this atom in order to turn it into a positively charged ion, and that is going to require some amount of energy. And I'm going to remove that electron right there because it is the highest energy electron. It is the weakest held electron because it's in the valence level. And so I'm going to remove that electron right there from the valence level. And in doing so, I have to overcome the attraction between that negative electron and the positive nucleus. Remember, the only reason that these electrons are hanging around at all is because they are attracted to the positive charges in the nucleus. So I have to somehow pull this electron away from those positive charges. And pulling it away from those positive charges will require some energy to do. So I have to take this electron and I have to move it away from the atom, pull it away from the atom, and in doing so, I go from the neutral lithium to a positive lithium cation plus a lone electron off by itself when that electron is pulled away. So there's a chemical equation that represents what I just did. I started with lithium alone by itself, so we can signify that it was alone by itself by saying that it was in the gas phase. And then I produced a positive lithium cation, which also would have been in the gas phase, and a single electron alone by itself. And the energy required to do that is the ionization energy, or the ionization potential. Now, if I wanted to, I could also pull another electron away from that ion and try to make it a lithium 2+ ion, but that starts to get very difficult to do because now I'm trying to break a filled valence level, the 1s valence level. So the first electron that I pull away requires an amount of energy that we call the first ionization energy. And the second electron that we pull away requires a second amount of energy, which we call the second IE, and so forth. In this class, we're only going to focus on the energy that it takes to pull away the first electron, and so we're only going to focus on the first ionization energy for elements. Now, this happens a lot easier for metals than it does for nonmetals, because we know that metals energetically prefer to lose their electrons anyway. So it doesn't take very much energy to make this happen, but it does take some energy, some ionization energy. However, we could also force it to happen with a nonmetal. Nonmetals do not like to lose their electrons, so we would expect it to take a large amount of energy to pull an electron away from a nonmetal, but you can do it. So down here, it asks for the chemical equation, like this one, that corresponds to the first ionization energy of fluorine, and this is the chemical equation that corresponds to the first ionization of lithium. I would like for you to write the chemical equation that corresponds to the first ionization of the element fluorine, following that pattern, and write it right there. Pause the video and do that, and when you resume, I'll fill it in for you. All right, returning to the video here. The first ionization of fluorine, we are going to pull an electron away from fluorine. We're going to start with fluorine in the gas phase. And we are going to engage in a process that results in a positive fluorine and an electron. So there's the chemical equation that corresponds to the first ionization of fluorine. Now, as I said, this does not happen easily for nonmetals. So for fluorine, it energetically prefers to gain an electron, right? Fluorine is not going to want to lose an electron. But we can write the equation for it losing an electron. We just have to recognize that's going to take an enormous amount of energy to make that happen, because nonmetals prefer to gain electrons rather than to lose them. So here I've given you two examples of elements that are undergoing their first ionization by losing an electron, a metal and a nonmetal. And I've mentioned that the metal is much easier to ionize by losing an electron than the nonmetal is. So the first ionization energy of lithium would be a much lower energy requirement than the first ionization energy for fluorine. Well, what are the factors that affect whether the ionization energy is high or low, relatively speaking? They're the same factors that affect an atom's size. So factors that affect the ionization energy are similar to the factors that affect atomic and ionic radius. And that should make sense because an atomic radius is just how tightly the electrons are held toward that nucleus. And the tighter that electrons are held toward the nucleus, the more difficult it would be to pull one away, and therefore the higher the energy requirement. Okay, so let's go over these factors that we have seen before when we talked about atomic and ionic sizes, and now apply them to ionization energies. So the factors that affect ionization energy. So the highest priority factor, and this rule always wins, is that the higher the N value of the valence energy level, generally the lower the ionization energy that is needed to remove an electron. So let's take a moment to think about why that is. If I'm comparing lithium and sodium, We know that sodium is a larger atom than lithium because sodium has an extra shell around it at the N equals 3 valence level compared to lithium, which only has the N equals 2 valence level. If sodium is larger, that means its outermost valence electrons are further away from the nucleus. Its electrons that are in those valence orbitals are larger orbitals, and therefore the electron is spending time farther away from the nucleus. So the general trend is the larger the atom, the easier it is to pull an electron away from it, because the electrons are further away from the nucleus. So as I go down a row and increase the valence levels from 2 to 3 to 4 to 5 and so forth, the valence electrons are further and further and further and further away from the nucleus, and therefore they experience less attractive force to the nucleus, and therefore it's easier to remove those electrons away, and therefore it requires less energy to do so. So the ionization energy is lower for the higher N value of the valence level. And just as with atomic and ionic radius, this rule number 1 is the highest priority. It always wins. If you are comparing two atoms in the same row and they have the same N value for the valence level, then it's a tie according to rule 1, and we go on to rule 2 the same way that we did for atomic radius. And rule 2 says that the greater the ZEFF, that is a technical way to refer to the effective nuclear charge, the Z effective. We know the Z number is the atomic number, and then that subscript EFF means the effective atomic number. So it's the effective nuclear charge, which is based on the total number of protons. So here again, we have the number of protons. Well, the more protons that you have in a nucleus, as with atomic size, it makes the atoms smaller because the electrons are held tighter to the nucleus. So as you increase the number of protons, you are increasing the attractive force on the electrons, and therefore it is harder to pull an electron away, and therefore the higher the ionization energy. So let's take a look at what that looks like. So as we go across a row from lithium to beryllium, their valence level is the same. So according to rule 1, I cannot tell which has the larger ionization energy. So I go to rule 2, and rule 2 says the more protons I have in the nucleus, the tighter the electrons are held. Lithium has 3 protons in its nucleus, beryllium has 4 protons in its nucleus. So beryllium has 1 additional proton in its nucleus that's holding onto its electrons tighter, and therefore the ionization energy required to pull an electron away from beryllium is a higher energy requirement than for lithium. Now, as we saw with ionic size, sometimes we have the same N value and sometimes we have the same total number of protons. And that required us to go to rule 3 and look at rule 3, which is the valence subshell effects, which is to say the electron configurations of the electrons in the valence subshells. And for ionic size, we mentioned this one right here. Paired electrons repel each other, and therefore it expanded those valence orbitals. But now there are 3 sub-rules in rule 3, and I will list them here in order. So now we are talking about the valence level only. We're talking about the electron configuration in the valence level only. And these factors can show when an electron is easier or more difficult to remove. So the first sub-rule in 3A, an electron in a higher subshell will be easier to pull away. If you have an electron that's in a higher energy subshell level, it's going to be further away from the nucleus and easier to remove. So if it's easier to pull away, then that means it's a lower ionization energy. The second sub-rule in Rule 3 is 3b. If you have a filled shell or a filled subshell, those are more stable. And if we are trying to remove an electron from a filled shell or subshell, it takes additional energy to break that stability. So if you have a filled shell or subshell, we have higher ionization energy required. And then finally, the third sub-rule under 3 is 3c, and we've seen this before. Paired electrons repel each other, they push away from each other, and if two electrons are paired in an orbital, one upspin and one downspin, and they are already pushing each other apart, then it's going to be easier to remove one of those electrons. So paired electrons repel each other, and that makes the ionization energy lower, because it's easier to remove an electron when it's already trying to be pushed away by the other electron in the pair. So as we think about these factors that affect the ionization energy of an atom, you can see how they are basically just the same factors that affect atomic and ionic size. The higher the N value of the valence level, the number of protons in the nucleus, and some specifics of what is going on with the electron configuration in the valence subshells. Why are these related to size? Because an atom's size depends on how tightly or how loosely those electrons are being held. So I've got some practice problems here. Why does magnesium have a higher ionization energy than sodium? So we have magnesium and we have sodium. And I would like for you to consider these three factors in order of priority, 1 and then 2 and then 3. And I would like for you to answer this question. Why does magnesium have a higher ionization energy than sodium? And another way of saying that is, why is it harder to remove an electron from magnesium than it does to remove an electron from sodium? So I'd like for you to pause the video as you consider the three factors that we've talked about here and decide why magnesium has a higher ionization energy than sodium. I'm telling you that it does, so you tell me why that's the case. Pause the video now and see if you can come up with a rationale for that. And when you're done, resume the video and I'll walk us through this. All right, coming back to this question, I'm telling you that magnesium has a higher IE than sodium, and I want to know why. So let's take a look at our factors here. Factor number 1, the higher the N value of the valence level, the lower the ionization energy required to remove an electron. So let's look at sodium and magnesium. They're in the same row. As neutral atoms, they have the same valence level. So in Rule 1, they are tied. So Rule 1 does not answer my question. Rule 1 doesn't help me answer the question. Let's go on to Rule 2. Rule 2 says, the greater the effective nuclear charge, which is to say the greater number of protons in the nucleus, the higher the ionization energy. Why? Because this is greater attraction. For those electrons that has to be overcome. So if we look at sodium and magnesium, we see that magnesium has one extra proton in its nucleus. So the magnesium nucleus is holding on to the electrons tighter than the sodium nucleus. And as a result, it requires more energy to pull an electron away from magnesium because there is a greater effective nuclear charge, positive charges down in the nucleus, due to that extra proton. And so that's why right there. So Rule 2 gives us our answer. Magnesium has one extra proton in the nucleus. So electrons are held tighter. So what does that mean? Higher IE, ionization energy required to remove an electron. Higher ionization energy required to remove an electron because of that extra proton down in magnesium's nucleus. So as we wrap up this video, I just want to emphasize a couple of general trends that we've noticed here. In general, when you have an atom that is smaller, you have an ionization energy that is larger. And the reason is because the factors that cause an atom to be contracted, that pull its electrons tighter to the nucleus and make it smaller, make it more difficult to pull one of those electrons away. So it increases the ionization energy required. So I'm going to make a little note of that. The general trend, and as I did with atomic size, I'm going to draw a sketch of my periodic table. Like so. And the general trend is that ionization energy increases as we get smaller and as we add more protons. So the general trend is that ionization energy increases as we go up a column, up a group, and across a period, across a row, to the right. And you will recall this is exactly the opposite of the general trend of atomic size, which generally gets larger as you go left and down. Now I emphasize that this is the general trend, and I want you to notice general trend because there is an important set of exceptions to this. So the general trend is basically described by the first two rules. This is rule 1 that talks about the N value of the valence level. And this is rule 2 that talks about the number of protons. And as I mentioned, there are important exceptions to this general trend. And the exceptions occur to this rule 2. In some cases, it is not a smooth transition to more and more and more and more ionization energy. There are exceptions to that general trend as you go across a periodic table, where ionization energy actually decreases as you go from one column to the next.